Hi everybody. This is statics lecture number 7 and we are talking about section 2.4 in the textbook. I had originally thought that I would do section 2.4 in one lecture, but on closer inspection I realized that I needed to introduce some very preliminary concepts in one lecture and assign a few problems and then do the full Betty in the second lecture. So 7 and 8 will both revolve around section 2.4. Now if you look at our class Moodle page, you will see that section 2.4, lecture number 7, and lecture number 8 will both involve section 2.4. And the topic of 2.4 is forces in space. So up to this point we have kept our discussion to the plane of the board, the XY plane, and now we're going to extrapolate that discussion into 3 dimensions. If you take a look at the assignment, I've put up all of the homework assignment for chapter 2. So some of this is ahead of our lecture today, but when we get to this point, to the 6th problem set, these will be the last problems for the entire chapter. So this will take us through today and all of next week. So my advice to you when you are working through 3-dimensional vectors is to rely very heavily on the math, and the vector math specifically. If you try to do it by visualization, you will run into trouble because it's just a little bit too complicated. So I'm going to teach you very much step by step how to go through this process and to be successful in doing a full 3-dimensional statics analysis. So the slide that's on your screen right now is titled Rectangular Components in Space. What we're talking about here, instead of having the XY plane, which is still the plane of the board, or the slide in this case, the z-axis is drawn out and slightly to the left, indicating that it comes out of the page toward you. So in other words, the XY plane is still the piece of paper or the slide that we're working on, and the z-axis is perpendicular to that, straight out, so that the horizontal plane is the xz plane, and then we have 2 vertical planes, the yz plane, which comes out of the board, and the xz plane, which is, or xy plane, excuse me, which is still in the plane of the board or the piece of paper. So we have a couple of vectors that we're going to talk about, a couple of angles and the angular relationship to the axis and also within a plane. Now, if you remember, when we had 2 axes in a plane, a force only had 2 components. One would be in the x direction, one would be in the y direction. When we're in 3 dimensions, we can talk about components in 2 different ways. We can talk about the component in a direction, such as x, y, or z, or we can talk about the component within a plane. So as you see here, this force F makes an angle which we call theta y with the y-axis. And then we could also think about it as making an angle not with an axis, but with the xz plane. In other words, if we just tipped it straight down into that horizontal plane. So then we would have a different sort of a component. It's a 2-dimensional component, which actually would look a lot like the previous 2-dimensional vectors that we've worked with. And then we turn it along an angle phi to get to an axis. So this angle would be phi, and the angle from here to here would be phi minus 90. The angle from here to here would be theta minus 90. So in general, we use theta to talk about the axis that we make with an, the angle we make with an axis, and phi to talk about the 2-dimensional component of a 3-dimensional force and the angle that it makes with an axis. So when we look at this, we can also think about the horizontal force, and this is the horizontal component of the force, which is that force within the plane, and then the vertical component, which in this case is made with the axis. So like we said, when we come down to here, F sub h, which is in the plane, this is really similar to what we've already worked. We have an xz plane this time instead of an xy plane. We have a force component within that plane, and then we can resolve it into axial components. And ultimately, that's what we want to do. That's where we're going to be able to start doing our analysis. So here we just talk about Fy and Fh. So this Fh could also be thought of as F sub xz. In other words, the component in the xz plane. So if you have a single subscript, x, y, or z, that's with an axis. If you have an h or sometimes a v, or two letters, in this case it could be xz, that refers to the component within a plane. So fx, if we want to resolve it then into the x component, this looks like a misprint. I'm going to have to think about this for a minute. But the x component is the f sub h times that angle, which is phi, the cosine of that angle. And f sub y is f sub h times the sine of phi. This f sub y is a misprint. That should be f sub z, because we're talking about the component along this axis. The rest of the work is, this should also be a z right here. And that's just from a change in axis that your authors had made. So remember, this is f sub x, but this would be f sub z. So at that point we have f sub y, which we resolved in this part of the problem. And now we have f sub x and f sub z. All right, so this is just another way of looking at this a little bit more in depth, where we start talking about this idea of unit vectors. Now, we know that we have I, j, and k. We know I, j, and we're adding k. So I is the unit vector in the x direction, j is the unit vector in the y direction, and k is the unit vector in the z direction. This is very standard in physics and mathematics to use that nomenclature. So we can say that the entire force can be described as the component in the x direction times the I unit vector plus the component in the y direction times the j unit vector times, or plus the component in the z direction times the k unit vector. So we can factor out F, which is the magnitude of the force. Notice the difference. Arrow indicates vector, no arrow indicates scalar, times the directional cosines along each axis. Now, directional cosine on each axis refers to not the plane, but the axis. Okay, so once again, we're talking about thetas from the previous slide. And then we call this vector comprised of the cosines with each of the axes a unit vector called lambda. And lambda is a vector that has, it's a unit vector, so it has a length of 1, and it's in the direction of the vector f. So f times this unit vector, which is itself the directional cosines with each axis, is called lambda. So the magnitude of f times lambda will actually give you the vector description of that three-dimensional vector or force. All right, so when we have two different points, here we have M located at xyz1 sub 1 and N xyz2, we can draw a vector joining the two basically by subtracting the x coordinates, the y coordinates, and the z coordinates. Then what that will do is it will give us a distance in the x direction, y direction, and z direction. So if we take 1 over d, this would be the distance, the entire length, times these, which are essentially the numerators of the directional cosines. We can write the f in the x direction, the y direction, the z direction as the product of f times d sub x over d, d sub y over d, d sub z over d, which are essentially the directional cosines. So in other words, from this drawing, we can get all the information we need to do that analysis. All right, so this is a sample problem, and on the next lecture, I will work a problem very similar to this. But basically, we have a transmission tower, and it's anchored into the ground, and then these are just the fragments, but we have a third guy wire holding it up. And this is a pretty common configuration. So the tension in the guy wire is 2,500 newtons. Now that is not a vector, is it? That is a scalar. That is the magnitude. The direction is along the guy wire. So we want to find F sub x, F sub y, F sub z of the forces acting on this bolt at A, and the directional angles defining the force. Well, the good news is we have the dimensions. We have the dimension in this direction, which I would assume, using the last scale, this would be the x direction. So we're going 40 meters from this point to this point, or 40 meters from this point to this point in the negative x direction. Then we are going from A back to B in the z direction, 30 meters, which doesn't look to scale, but that's okay, and then 80 meters in the y direction. So once we have those lengths, after we take our diagram and we pick out the lengths, we're going to be able to do the rest of this work. All right, so the distance from A to B, then, we have negative 40, right, in the x direction from here to here. We have negative or positive 80 in the y direction, in other words, from here to here. And then we have positive 30 going from here to here. That's a little harder to see, but basically point B is in front of point A. So we find the length using a three-dimensional theorem of Pythagoras. We square each of those x, y, and z components of the length, take the square, add them together, take the square root, and then we have the length. So that means we can find the unit vector along the guy wire by taking each of the components, 40, negative 40, positive 80, positive 30, and dividing each of them by the total length. So this is cosine theta x, this is cosine theta y, and this is cosine theta z. Then by doing the division, we can calculate the component I, j, and k of lambda. All right, well, once we have lambda, we can multiply it by the magnitude of the force F to find the vector force F. So we multiply 2,500 newtons, which is the magnitude of force F, by this unit vector, lambda, in the direction of the cable, and we write an expression then in newtons for the force vector. So that tells us what the force is along this guy wire in each of those directions. Now, if you took each of these numbers, squared them, and added them together, and took the square root, they would multiply up to 2,500, or they would add up and take the square root. The value would be 2,500. Similarly, if you took, this is a unit vector, right? So if you take this and square it, add it to this squared, add it to this squared, take the square root of that, the value of that would be 1. So the value of the force vector F, the magnitude, is 2,500. So the magnitude itself is 2,500, and the magnitude of lambda, the unit vector along that cable, is 1. All right, well, after we do that, we can realize that these are the cosines. So if we take the inverse cosine of this, we can find the theta x, which is right here, theta y, which is right here, and theta z, which is right here. So we can find all of the stuff by going back to that screen, measuring. It all starts with this, these measurements, the dimensions on your drawing, and the magnitude of the tension. So when we work problems, these problems are quite lengthy, but we'll go through them step by step and make sure that you are confident of your skills at every step. So thank you for your attention, and our next lecture, lecture number 8, we will delve into the mechanics of this, but in the meantime, I've assigned a few problems for you to get started on that. And if you look in your textbook, the problems that will get us started on this in Chapter 2 are the problems at the end of Section 2.4. And all of these problems, the last 3 or 4 sets, are at the end of Section 2.4. But for today, we're going to be talking about the 4th problem set, 272, which is finding theta x, theta y, and theta z for a force, just like we did in this homework problem, in the problem, the sample problem. Problem 278, which is similarly finding the theta values for the directional cosines, which will be for next time. I'm sorry, that'll be for this. We're doing 244 and 272. Sorry, got mixed up. So 272, 278, and 280 are the homework problems for this set. 290, we need to do, I'll do some example problems on the next lecture to get you ready for doing 290 and 298. And then similarly, we'll do some sample problems that will get you ready for 102, 106, and 112. All right, well, have a great day, and we'll see you later on lecture number 8.